Calculus is actually a Latin word which means small pebble. And in fact, it still means that in the medical world today. But to the Roman, calculus really meant calculate. In fact, that's where the word calculate comes from. Calculate, calculation, calculator to us today. It was all because small pebbles were originally used for counting and working out sums. However, although the roots of calculus go back to Archimedes and before him to Eudoxus, that's 300 BC, right, and through various Arab mathematicians, and some work was done through Indian mathematicians who probably learned it from Persian mathematicians, and separate work was done in China. In its fully fledged form, that's only 300 years old. It's an amazingly powerful and interesting way to do mathematics. It's used hugely by engineers, by scientists, by economists, and in all sorts of ways today. There would not be a space station. There would not be big modern buildings. There probably wouldn't be the phone in your hand without calculus. So let's begin. Consider, if you would, the function f of x equals 3x plus 4. And if I said, could you do a sketch of that function? Could you work out some values for f of x, for different values of x? You'd say, of course I can. Right? If I work out that x is 2, and you'd say, well, I can work out f of x because I'll just do 3 multiplied by 2 add 4. And I say, well, let's not do 2, let's do 6, let's do 8, let's do 93.5. You can work out the f of x value each time. Well, what if I said, let's not talk about f of x equals 3x plus 4, but let's talk about y equals 3x plus 4. Can you work out y coordinates that go with that x? You'd say, yes, of course I can. I'll put in x is 2, I'll put in x is 7, x is 10, x is 93.5, and for each time I do that, I'll multiply by 3 and add 4, and I'll get the y coordinate. You say, well, wait a minute, that's the equation of a straight line, and we could plot the points and get a straight line. You say, I know the gradient must be 3. I know that the intercept is at plus 4, because that's what happens when x is 0. Okay, so that's my 4 there. Right, and this is my graph y equals 3x plus 4. And as we said in the straight line section, we call that the origin. We always label the x-axis. And you will now find that sometimes, in questions you're doing, instead of labeling this with a y for the y-axis, they might label this as f of x. Because they're using the equation in the form f of x equals 3x plus 4, which we've seen in the past as functions, but it's also the same thing as saying y equals 3x plus 4. If I said, what's the gradient of this line? You'd say, I know it's 3 because 3 is a coefficient on x. That's what we do with a straight line. And that's what people have been doing for hundreds and hundreds of years. But the question arose, what happens if it's not a straight line? Here's a function, f of x equals x cubed, take away 3x squared plus 7. And if again I said work out different values of that function, you would plug in different values here. Simplest one being 0. Oh, f of x, 0 cubed minus 3x times 0 squared plus 7. Oh, if I'm doing it as a graph, if I'm doing y equals x cubed minus 3x squared plus 7, and I put 0 in for x, oh, that would give me this coordinate here must be 7. This is what the graph roughly looks like. Okay, and again, if I said sketch that graph, you could pick different numbers for x, work out the y coordinate, which is the same thing as f of x, and do that. And again, sometimes on questions, again, I've here put x, and I have called this the y-axis, but they might just say, instead of writing out the equation of this graph next to it, x cubed minus 3x squared plus 7, especially when we're short of space like we are here, we can just say y equals f of x. It's just the values of the function. But what if this time I say, what's the gradient at this point here? And what about the gradient here, or here, or here? Here the gradient is quite steep, it's positive. Looks like here it's turning, that's momentarily horizontal, the gradient is 0. No, the line's going down, the gradient is negative. Looks like the gradient is 0 again, and it's going up. And if I want the gradient at this point, that's the same thing as the gradient of the tangent to the curve, the line that just comes up and just touches the line once, the curve once here. The tangent there. The gradient of the tangent is the same as the gradient of the curve at that point. But if I want to do, of course, work out other gradients, then that would be lots and lots of gradients of lots of different tangents. Calculus does two things in the main. It lets us work out gradients at any point on a function, and also lets us work out areas underneath a curve precisely. And from extending that, volumes of shapes which have a curved surface at the top. The area between the curve and the x-axis, or if I was thinking in 3 dimensions, the area between a curved surface and a horizontal surface underneath. The volume, sorry. Very, very powerful. And as I say, used in all sorts of ways in the modern world. How's this done? Well, that's what we use differentiation for. Differentiation measures how fast something is changing. Now, we're beginning the notes for differentiation on page 2, so we're going to leave page 1 for the moment, but you might want to make a note of this, say on the back of page 1, so it's opposite page 2 for reference. So, as I say, differentiation is a measure of the rate of change. For example, when you buy a car, or if you're an avid fan of Formula 1 or something, how quickly the velocity, the proper word for the speed, the velocity changes, what's the 0 to 60 of the car, how quickly it can go through that change is a rate of change. The acceleration then, how fast the velocity is changing, that's a form of differentiation. You could argue, those of you who do physics perhaps, oh, but wait a minute, velocity, that's how fast distance is changing over time. Yes, so velocity is a rate of change. It doesn't matter if we're talking about the rate of change of distance, or of the rate of change of velocity, or the rate of change of the price of bananas. Rate of change is what differentiation is all about. And on a graph, that's the same thing as the gradient. Gradient tells us rate of change. So differentiation lets us know rate of change, even if the graph and the gradient is constantly changing. So it's the rate of change at any given instant. It is connected to the formula of the graph, and so because it comes from it, or it derives from the function, it's known as the derivative of a function. This bit's already in your notes, and it's normally written as f dashed x if it connects to an f of x, or if the formula is written as y equals, we sometimes write dy by dx, which stands for change in y over change in x at that instant. So hence why it connects to gradient. Change in y over change in x at an instant, even if the gradient is continually changing. Occasionally you get other words like d by dx, f of x. Again, it just means this bit means differentiate the function to get the derivative. But mainly it's in these two ways here. So let's consider the rule and some examples. So on page 2 in your notes, if a function is equal to, we work out the function by x to some power, x to some number. How do we get the gradient? How do we get this derivative? Well, the formula for it, which connects to f of x, so we write it as f dashed x, multiply by the power, and obtain a new power by taking one away. Please fill that in your notes. This is very, very important and very, very powerful. Here's how it works. Now, if the question says work out the derivative of x to the 5, don't please write x to the 5 and then equals and an answer underneath. We are going to multiply by the power, so I'm going to say it's 5x, and I'm going to take 1 away to make that 4. That's the rule for how we get the derivative, how we differentiate. But it is not true to say x to the 5 equals 5x to the 4. And that's a very common mistake when people are doing differentiation. So, whether or not the question says f of x equals, you do always put f dashed x or dy by dx. But for just now, f dashed x equals the derivative equals. So, when I wrote down question 2 here, I actually didn't put in the f of x, but I would still write f dashed x equals, and then it's understood that this is the f of x. Always please put in f dashed x. Do not say this 2x cubed equals the answer I'm going to write here. That's not true. Multiply by the power. Oh, so there are 2 there already, but multiplying by the power, 3 times 2 is going to give me 6. Multiplying it all together. X, take 1 away from the power, squared. Very simple. On example number 3, f dashed x equals. Now, we're just going to do these as 2 separate things, but let's make it a little bit trickier. So on your notes, change this power, please, to -3, because negative numbers should not face us at all. I'll just do one term at a time when there's pluses or minuses in between. So x squared multiplied by the power 2, take 1 away from the power, x to the power of 1. You can write the 1 in, but we don't need it. 2x means 2x to the power of 1. Multiply by the power, -3, multiplying the 4, -12, which I'll write as that. Take 1 away from the power. Please do not call that -2. -3 take away 1 is, of course, -4. Example number 4. My f of x is 4x to the 4 plus 3x. Again, let's make it a little bit trickier. So why don't we put 1 over 6 as my power, as my index number there. Again, make sure you write in, f dashed x. I'll take them one at a time. Multiply by the 4. 4 4s 16. X to the power of 3. Multiply by the power. 1/6 times 3. Well, that's 3 over 1. 3 times a 6 is 3/6. Oh, which is a half. X. Now, I'm going to make sure it does not look like the x is next to the 2. So this line is horizontal. It's not a forward slash. And the x must be no lower than the middle. It could be up next to the 1, but it must not go down next to the 2. It's a half x, because the 6 times the 3 gives me a half. And, a 6, take away 1, 1/6, take away 6/6, -5/6. Okay, let's put the f of x back in again, because we should be used to seeing it both ways. My f dashed x, my derivative, my rate of change is 3x. Okay, that's x to the power of 1, since there's no number written in. I'll multiply by the power. So 1 times 3 is 3. Take 1 away from the power. X to the 1, take away 1. That's x to the 0. X to the 0. Oh, well, that's just 1. So I'm just going to write the 3. I'm not going to bother it. I could write x to the 0, but that's pointless. Differentiate my 4. I don't see an x term there. That means it's actually x to the power of 0. Oh, and multiply by 0, 0 times anything is 0. Oh, so that just vanishes. So my f dashed x equals 3. This makes complete sense, because if I said y equals 3x plus 4, what's the gradient? You would tell me the gradient is 3. See, I've known that ever since I did Nat 5. Gradient, the number multiplied by the x, is 3. So of course, if the gradient is 3, and f dashed x tells me a formula for the gradient is 3. Because this particular formula was for a straight line. The rule always works, whether it's a straight line or a curve. Even when it's tricky. This is why we've been doing some examples on the meaning of indices. My f of x is a half x to the negative 10. My f dashed x multiply by the power, negative 10 over 1 times a half, that's negative 5. X, take 1 away from the power, negative 11. You'll notice I put this in as example 7. There is an example 6 in the notes, which we'll come back to next time. Example 8. F of x is, now if there is a root involved, we're not allowed to differentiate something when it's underneath a root. So I need to rewrite this without the root sign. So this is still f of x. This is not f dashed x yet. I've not differentiated. I'm just going to rewrite this from what we've said before on indices, x squared, when we write roots as a fraction. This is the same thing as saying x to the 2 over 5. There's no root involved now. Now it's in a form that I'm allowed to differentiate. So if we have a root sign, we have to get rid of the root sign. But once I rewrite it as this form, now I can say this is f dashed x. This is me differentiating. Now I'm going to multiply by the power, 2 over 5, again, horizontal line, x no lower than the middle, so I'll actually put it above. Subtract 1 from this power, 2/5, take away 1, take away 5/5, negative 3/5. There's my answer. Multiply by the power, take 1 away from the power. The actual differentiation rule, the calculus rule, is easy. It's the Nat 5 bit that's the trickier bit. And so what about something like this? Not allowed to differentiate when there's a root. We're also not allowed to differentiate if the term we want is underneath a fraction. But we know how to bring something to the top. That's why we've already been looking at examples with negative powers up here. So, my f of x, this becomes 2 over cube root x, that's x to the 3rd. Excuse me. Still can't differentiate because the x term is underneath. So my f of x, bring it to the top, 2x, change the sign of the power. Of course, if there was a number, a coefficient in front of the x, I would leave it underneath. I don't know, if it was a 5 or something, I would write 2/5 and bring the x term up. Now I can differentiate f dashed x, multiply by the power, 2 over 1 times negative 1/3. That's negative 2 over 3. Take 1 away from the power, negative 1/3. Take away 3/3, negative 4/3. The indices bit you can do, and you'll get used to these tricky ones with practice. The actual differentiation rule, multiply by the power, and subtract 1 to get a new power. That's what differentiation is all about.